So quite often in physics, we will want to take a state or take a function and break it down into its component parts to extract some kind of useful information. You can build up quantum states from your energy eigenstates sometimes. You can build up functions from your basis. And so if we have some vector v and we plot it on our Cartesian coordinates, x and y, here's our vector v. If we wanted to find just the x component of this vector, we would need to take the projection with the x-axis. Or in other words, we need to find the overlap between our vector v and our x hat vector. And the way that we're going to do that is we take the dot product. V dotted with x hat will give us this stretch right here. Another way we could write this, a way we could generalize this, is we take the inner product of x hat and v, or if we have some general orthonormal basis, we take the inner product of en with v. So these are our basis vectors. We take the inner product with v, and that finds how much v overlaps with each one of our basis vectors. We're projecting v onto each one of these basis vectors. So when I wrote this down, I said this is some orthonormal basis. So we should talk about what that means and think about why that's important. So I'm going to go ahead and take the inner product of just two random basis vectors. I'm going to call them phi. And if we do that, we'll see what kind of result we get and then which conditions give us that idea of orthonormality. So we're going to be dealing with our basis, which is a set of functions, phi n of x. These basis functions need to have an important property in order for us to be dealing with these inner products well. We need phi n, and if you'll excuse this poor notation, we'll need phi n to vanish at positive and negative infinity. You can't really plug in infinity into the arguments, but this is a nice succinct way of writing it. So if we had two basis vectors from this set, we're taking phi m and we're overlapping it with phi n. Then we can take this inner product and we can just write this as an integral. This would be equal to the integral from minus infinity to infinity dx. We complex conjugate what's in the bra, phi m star of x, phi n of x. And so this will equal some value depending on how much these overlap. And then we'll also have a delta and m in here, a Kronecker delta. So this Kronecker delta tells us that if our basis is orthogonal, if all of our basis vectors are orthogonal to each other, if you take the dot product of two things that are orthogonal, you get 0. If we have basis vectors that are orthogonal, and we take the dot product of two different basis vectors, we should get 0. So this is 0 if n is not equal to m. But if it is equal to m, then we just get 1. And so all that would be left over is this normalization constant. So if all of our CNs are equal to 1, our system is orthonormal. Meaning All of our basis vectors are orthogonal to each other, and they're all also normalized. So why is this important? Why does basis projection matter and depend on having an orthonormal basis? Well, if our basis vectors start to overlap, then our state or our vector is no longer uniquely defined by our basis.
What I just said isn't precisely correct, so let me try and clear this up. If our system has an orthogonal basis, that means that our basis vectors are linearly independent from each other, which makes our system uniquely defined. However, if our basis is non-orthogonal, that doesn't necessarily mean that the basis vectors are linearly dependent, but we can't use the inner product to find the coefficients on our basis vectors. We can't do all of this overlap stuff.
So we want our basis to be orthonormal so that we get consistent results and our system is uniquely defined by the basis. So let's write down some things we can do if our basis is uniquely defined by our orthonormal set. So if we have f of x, and we can expand this in terms of our basis vectors, or in other words, we could write this as an phi n of x. Remember, implicit summation here. We could also write this as our state f is equal to an times basis vector phi n. All right, so if we want to find these coefficients, that's something that's very useful to us, right? If we have some state and we don't know exactly how it's built from our basis set, then finding these will give us very valuable information. So if we want to figure this out, we need to take our basis vectors and see how they overlap with f. Or in other words, we need to take phi m and project it onto f. Or if we plug in this definition, we would have phi m an phi n. So this an is just a number. This can come out in front. And if we do that, we're then just looking at how our particular basis vector overlaps with another one. And if we have an orthonormal basis, we know what that should be. The inner product of these two should be our Kronecker delta. So let's go ahead and write out what this would be. Our an is something that we could just pull out of the inner product. If you don't believe me, you can write down the integral and you'll see we can just pull it out of the integral. So we'll have an times delta n m. All right, so what this means is we have our an, and this is only going to be non-zero if these are the same basis vector. So if n is equal to m, we get our an. So in other words, if we wanted to solve for this, we know that all of our n's in this line have to be equal to the m's in this line. And so we could rewrite this. We get 0. We oftentimes will just write out the terms that are not 0 in order to save us some baggage. So this would be phi n, inner product with f, is equal to an. So this is very powerful. If we want to figure out how to expand our state in terms of basis vectors, we just need to take one of our basis vectors and whack it on the state, evaluate this integral, and that will give us our coefficient.